Welcome to this lab. My name is Stan Gilenji. I'll be taking you through advanced encryption algorithm, and I hope you have watched our previous videos and you have subscribed to the channel, and also you'll be able to share some of the things that you're doing here to share knowledge as to these key concepts for cryptography. So in this topic for advanced encryption algorithm, so we look at analyzing the operation of the AES algorithm. I also want to explore the application areas of AES algorithm. And in a previous video, you're able to see that we're able to classify these as part of SKC algorithm. The algorithm that use the same key to encrypt, the same key to decrypt. And also we're looking at this as a way of addressing the security services, that is confidentiality. And with doing that, able to achieve or to mitigate against passive attacks where you're dealing with ensuring that the confidentiality of data, and also things like eavesdropping. So AES algorithm, it's also known as a regional algorithm. It's a symmetric block cipher that takes plain text into blocks of 128 bits. But the good thing with this is that it provides you flexibility with the key size, because it makes use of 128 key size, 182, and 56. So depending on the computational resources, you can be able to select which would be best algorithm to execute with the resource that you're having. So it's considered to be the secure, it's a worldwide standard, and it's published in the FIPS standards. So AES design is provide this flexibility. So the generation of the secret key, how you're getting the plain text and creating the cipher. So you can either use 128 key size, 182 to 56 key size. So the beauty of this is that every time you're using this, you notice there'll be a change in the ciphertext. So the larger the key size, the stronger, the more difficult it will be for someone to crack that ciphertext. So how does AES work? So AES work in different ways. So it makes use of iteration. Most of the as SKC ciphers, majority of them uses a substitution and permutation, but AES uses form of iteration. It uses AES uses a substitution permutation or SP tables where you're dealing with a number of routes and iterations. So it makes use of an S box, which is usually a 16 by 16 matrix, and it's a 128 key size, take 10 routes. If it is using 182 key size, it uses 12 routes. If you're using 256 key size, it then makes using 14 routes to the encryption process. So you begin from here. You see that the encryption process will do the operation, does this operation, the subbyte operation, does a shift row operation, does mixed row operation, and add route key. But in the last round of computations, you notice that doesn't have the mixed row operation. So the decryption process takes the same cycle. You have that, and then that you do that and generate the key size for each to provide what we refer to as diffusion and confusion. Make sure that the relation between the ciphertext is as complex as possible, and there's the statistical property of the ciphertext. You cannot be able to determine the plain text of it. So the decryption process, it means that you're reversing back the process. So you do the inverse. If you did the shift row, you now do the inverse of the shift row. If you do the subbyte, then you use the inverse of the subbyte and add route key and inverse of mixed code. So you can be able to get back the ciphertext. So you can be able to transform the ciphertext back to the plain text. So there's a substitution. It makes use of S box. So in the first step, the byte of the block text is substituted based on the rules where you define and then putting information to what you refer to as a state. So the decryption process will convert that to be an inverse. So you do a checkup. So you check a value here, and then you read, let's say X, Y. Then you come to this table and you replace it with the value that is X, Y, and you take that value, and that will be that value for that. So this is our S box. It's a 16 by 16. So you read from X, Y, that value there. Then you go to the other table and you replace it with the X, Y. You read that value, and then you replace back to that value. So the decryption process will be using a reverse of such a table to go back to the original message. So these are the steps. The shift row is the second step is the shift row operation. So each of the 4 rows of the matrix is shifted to the left, but it makes the first row. The first row, the state that you create from the sub-byte operations, it undergoes the shift row operation. So the first row remains unchanged, meaning that whatever you had in the sub-byte operation, it's nothing you're changing on this side here. But the second row does one shift to the left, meaning that the value that is here will go to this position, and the value that was in this position goes to the next position, and this one will go to where the gap was created. So if you look at here, you are saying that this value move to that section, and then AC goes to where 63 is, 63 goes to where 50 is, and 50 goes to where initially 82 was. So that's basically what you're saying, that you're shifting that value to once to the left. So that is the second row. But for the third row, it means that you have to do 2 shift. So meaning that you move this value here to where 2C is, and mean 92 goes to where 83 is, and then the others take the previous positions where you have the 2C and 83. So the fourth row does thrice shift to the left. So it means that you're picking this value here and putting it back to where the third position here. So it means that these ones will go where 5.2 now goes to the initial stage, 2.3 goes to that, and then 4.4 goes to that position. So that's what we refer to as the shift row operation. It's the second operation that comes after you do the sub-byte operation. You see in the sub-byte operation you're using a S box. Once you get that state is usually transformed using these conditions. So in the decryption process, it is the opposite of that. Instead of shifting to the left, you shift to the right. So the mixed quorum is it makes use of the matrix multiplications. I'm sure you know every time you multiply, it makes use of a constant. It picks the odd. So this was the state that is created every time you do the sub-byte operations. So that state is multiplied using a specific constant. And if you know the matrix multiplications, every time you multiply 4x4 matrix, 4x4 matrix cannot be multiplied by 4x1 matrix, meaning that it create a new column. So if you do that, it creates a new column for each. If you do multiply the constant, it creates a new column for each and every odd state of what we had in the shift row operation. So then there's an add route key. I think these are operations that the key addition is also known the add key. There's one step in AES encryptions where the state matrix is combined with a route key to introduce a key specific information to enhance the cryptographic security. So that key is added at each and every row so that it can be able to be used to secure to make sure that the algorithm is withstand some of those possible attacks. So AES as various SKC operation mode, they operate in different modes. We have the electronic codebook mode, safer blockchaining mode, safer feedback mode, counters, and Garoris counter mode. So it's good to know which mode of operation we're using. In default, CBC is left as the default. If you're encrypting files, then it's better use a CBC, what refer to as safer blockchaining. Some of these things like counter or OFB, they are mainly used to do stream ciphers, things like voice. So every time you're choosing the mode of operations, it's always good to know what you're using it for. Because for file encryption, that is best used the CBC, which is a safer blockchain, which most of the system is left as a default mode of operation. AES application areas, I think, is mainly used compared to other encryption algorithm protocols. It's the most secure security protocol. It's implementing both hardware and software. It's been wide various applications. If you're doing the SSL, TLS, it's now used in device applications. And if you look at Google Storage, AWS Cloud Storage, and many popular apps are using AES encryption to safely send information such as forthcoming messages. It's one of the most secure algorithms. So every time you're using that your wireless communication, using WPA2 behind the scene is usually the AES algorithm. If you're doing browsing using SSL, security as a protocol, processor security, and general file encryption. So those are some of the application areas of where we can deal with, you can deploy AES algorithm. Thank you, and that's a brief overview of AES algorithm. More labs will be able to show you the practical aspect, to show you how the key size 128, 192, 256, and then how to select the various modes of operation.